Next, we have Nitish to talk about optimization of periodic fins using the streamwise periodic solver with isothermal boundaries in SU2.
Thank you. Hello, everyone. I'm Nitish. I'm a researcher at Vito, and I work with my colleague, Carlo. So I'm going to present to you today the progresses that we have done with the development of isothermal boundary conditions and to use that in conjunction with streamwise periodicity, and also some bonus results which is not captured by this caption. All of our motivation is that if we run Ninja, it should give us no error, but obviously we have other motivations as well. So in heat exchangers, they are often represented by geometries which have a repetitive pattern. And we can exploit this knowledge by maybe reducing the computational cost, right? So now instead of it's a standard plate fin heat exchanger where you have two sections, right? And you can see that these fins are repeating as you go in the flow-wise direction. So if you see, if you have such circular fins, you will have this kind of flow pattern over it. And at each of these locations, A, B, and C, you will have similar velocities, almost same velocities, and you will have a certain kind of periodic pressure, which would be going down, right? Because you will have pressure drop. So you will have a linear pressure drop, and you will have small variations along on this pressure drop, which will be nothing but your flow field, certain kind of periodic flow field over your fin. And if we exploit this information and we use it in the solver, we do not have to simulate, for example, 15 or 30 fins simultaneously, which can be very expensive. Instead, you can just do simulation of one fin and you can predict the performance of the entire flow field. So this can be very useful and it can be very groundbreaking, for example, in heat exchanger optimization. To go further, isothermal boundary conditions in conjunction with the flow equations, what I showed you previously, can be very interesting if we are designing an evaporator or a condenser where we have constant temperature properties. And for that, we need a new set of source terms that can, let's say, represent similar kind of flow behavior, but in a streamwise periodic flow. And in this case, the things are not linear, because if you look at the temperature profile, it has a bit of like a logarithmic curve or exponential curve, and you have small variations over that exponential curve. So it's similar to a pressure drop, but now it has an exponential variation. And thankfully, we can represent that with this temperature with this equation. So that means we can break it into two separate terms. So one is the theta term. So theta term is nothing but something like a reduced temperature, which gives you a flow field around this fin. And you have a lambda, which is your exponent, which defines how much is your temperature increasing or decreasing as you go downstream. And then if you plug in these assumptions into your energy equation, you get two source terms. So this is the laminar part of the source term, and this is the turbulent part of the source terms. And when you solve this in conjunction with this quadratic equation, you get the solution of an isothermal periodic boundary condition in a streamwise periodic flow. So this can be very, very useful, and this was already shown in the last presentation, in the last year's presentation. But today I'm going to show you more concrete results on this work, what we have done. So previously we showed a bit of a preliminary result on this, but now I'll show you something more concrete. Some homework first. So the code is already available. There is a draft pull request, which is open for around 1 year now, but there's still small fixes which is going on. And the work is currently develops on what Tobias has already developed in terms of flow source terms. I'm just complementing those flow source terms with the energy source terms. So over here, I'm showing you the temperature equations, the temperature solvers, the simulations from the temperature solver. And what you see on the left-hand side is the laminar source terms, and on the right it's the laminar plus the turbulent source terms because they are being simulated at different flow fields. On the top, you have the simulation of a 15 fin simulation, and let's say the 14th fin is then a streamwise periodic fin. And the bottom simulation is from a streamwise periodic solver. And there's order of magnitude difference in terms of the computational cost. Now, a bit of a exercise for you. So one of the simulation domain you can see, or the contours are a negative of the streamwise periodic, but that's because in streamwise periodic, I'm showing you the theta term, which is a reduced temperature, whereas in the fin array, you see the actual temperature. However, and in a similar case, you will see also in the turbulent case that they are a negative of one another. But if I just use this temperature to reconstruct the temperature field in the streamwise periodic zone, you will see that they overlap. And what I'll show you now is the data at each of the different sections along this fin. And if you see here, so again, yeah, UX pressure, I give kudos to Tobias for a very nice implementation. But for the temperature and the eddy viscosity term, you can see that the results obtained from a fin array simulation and from a streamwise periodic range simulation, they overlap on one another. So the implementation is correct, and we get a pretty good accuracy. This is what we can conclude from this graph. Obviously, we are interested in optimization. We are not going to just stop at analysis. This is the gradient validation plot for the laminar and the turbulent source terms. And you can see they match for most of the points. There are some outliers, but that's because I just ran finite difference with just one finite difference step. And obviously, once we have done that, we would like to look at the optimization. So over here, I'm using a CAD-based parameterization, very similar to what Prahash has mentioned. And we are running for two different flow regimes. So one is the laminar, the other one is the turbulent. And you can see it gives a bit of a shape, which looks a bit similar to what Prahash showed in the previous presentation. And for the turbulent case, also you see, yeah, like a bit of an elongation in the geometry. And what you see here, what I'm trying to maximize here is the lambda L, which is nothing but this exponential term that you have. So higher is the exponential term. That means higher change you get in one unit cell of your fin. And I'm trying to increase the mass flow rate as compared to the baseline and try to keep the pressure drop and the volume fraction of the domain same. Now I'll come to the shortcomings in a while, but let's also look at what designs we get from free-form deformation boxes. And you see there that over here, the laminar and the turbulent cases, they go more or less in a similar shape, but they have a bit of differences at the leading edge. You see it's more flatter over here, but they both elongate in a particular fashion. And what I found out later that perhaps free-form deformation box is a better option in this kind of in this particular test case, and that's primarily because if you look if you have seen the Prahash's presentation, in the CAD based, we have just one or two parameters that control the variation in the X direction. And the current setup of the problem with increase of lambda L, it would always like to increase in the X direction. And somehow the CAD, since it is just dependent on one design variable, it doesn't allow it to move as much because then it gets a lot of cross terms, which doesn't allow it to move that much. However, if I just go to FFD, now I have a lot of design variables that are independent only in the X direction. And that's why I'm able to increase my lambda L quite substantially while also maintaining my mass flow rate, which if you see, it's completely dependent upon the Y distribution of these fins. So it's a pretty interesting outcome. We are working further on it, and perhaps we will have some more results in the next SU2 meeting. So here we come to the bonus part because I wanted to also show something about topology optimization, but it was not incorporated in my topic of the presentation. So this work, let's say I should give kudos to Tom because he pointed me to the legacy code which he implemented at some point. And then what we have done is what I have done is upgraded these these codes to the latest form and added new objective functions and made it work also in a multi-zone framework. So I'll show you, and again, yeah, there's no PR as of now, but I hopefully soon, now that we have some verification and validation of this, maybe we can upload it. What I'll show you some results is for a manifold design in which the flow is going in and there are some, let's say, radiator pipes, and then the flow is going out. And what I'll show you is the design of these manifolds through topology optimization. So first of all, this is the very standard objective function, which is power dissipation in a flow field. And this is usually the objective function. I'll not go into a lot of details of this, but you can see a very you can see a very nice design coming in at the inlet, and also for the outlet, you get a particular kind of design. But obviously, in a manifold, are we interested in having a power dissipation? I mean, it's not all the time, because what we would like to do is to have a more even distribution of the fluid mass flow rate in each of these individual tubes, which is called as the maldistribution function. And if you look at the design that we get for the manifold for this particular case is largely different as compared to if we use a power dissipation term. And that's what we are experimenting is to see a different combination of these two objectives together, because both have their own benefits and shortcomings, primarily because we are using topology optimization. And you can see that you get a pretty nice manifold design. So at least some of the designs are very close to what they say there should be, let's say the analytical design of these manifolds. But again, yeah, the objective would be in future that we try to get certain designs and try to see if those assumptions still hold with the latest optimization tool that we have. I would also like to give courtesy to my colleague, Sanjay, who ran these simulations on my behalf. So conclusions and way forwards. So the 2D and 3D verification of the isothermal boundary condition for the streamwise periodic flow was done. What we would like to do is like really fine tune the optimization framework further so that we can obtain more consistent results in the future. Also to have a verification with a high fidelity solver, but now it has been pushed back as a more of a long-term goal. And then further, we try to increase the robustness of the topology optimization code and perhaps also open up draft PR on that. Thank you. If there's any question.
One question over here from Tom.
So, so where for thermal problems. So I'm curious if you are
that would be the next step. I mean, we have not looked at it just yet. I would also say that I'm an amateur in the topology optimization, so we are still spending a lot of time understanding it. But that will be the next step, that we put it with the thermal problem, and then we solve the solid along with the fluid. That would be the next step.
We were trying to grow space.
Yeah, that will be the next step. Yeah.
More questions?
So thanks very much for the vision of the method. Design for manufacturability is a concern both from Europe and the previous one when it comes to making the fence themselves.
I mean, that's definitely a shortcoming, yes, but we have, yeah. So there was a question, what is, there's a limitation with the manufacturing of these designs that we show from shape and topology, and how do you see that? Obviously, that's a shortcoming, but we have also internally additive manufacturing group who is looking into this, and I hope they will answer these questions for us. So.
More questions? Let's thank Nitish once again.